Hello. Yeah, it's 7 now. We'll wait for a few more minutes and then start. Yeah, let us begin. Okay, hi everyone. I'm Suchit Prabhu, PhD scholar at IIT Delhi, working with Sumit Agarwal and Manik Verma on extreme classification. Okay, so the plan for today is, we'll revise whatever was done this week, then solve a few questions, and then yeah, there'll be a coding demonstration of whatever was done this week. Okay, so let me share my screen. Is my screen visible? Is my screen visible?
Yeah, yes, sir.
Okay, fine. So can anyone go ahead and tell me whatever was covered this week? Then we'll go through each of the topics one by one.
We started unsupervised pre-training.
Ah,
Why unsupervised is because layer by layer, so input and the first hidden layer
okay.
will apply autoencoder. So since it's replication, that's why it
Uh-huh.
is unsupervised. We are not bothered about the output.
Mm-hmm.
And layer by layer, so all the layers are taken like that only,
Okay.
replicated using autoencoder.
Mm-hmm.
And at the end, the uh, once this all these, I mean, at every layer, the weights are getting fixed. So
Mm-hmm.
once it is done for first hidden layer and then second hidden layer, so once it's the weights are fixed, and
Mm-hmm.
then the entire network is we do it for, I think, test the entire network together we do for test, right?
So that is for
The
train. So
whole
once
network
pre
is,
yeah, so
yeah,
once pre-training is done, so we have a set of weights which are good to start with. We then train the
add the
entire
output.
network. Yeah,
Yeah,
we
we
train the
add the
entire
output
network on
and
the final task. Yeah,
final,
yeah.
yeah.
The task which is of interest to us. So once this pre-training is done, we train the entire network on the data
So
set.
the convergence was happening with this, uh,
Yeah, yeah.
but it is no longer used, this technique.
So it's used in context of transfer learning.
Mm.
So yeah.
Then different activation functions, but this led to the thought that okay, activation could be better, or
Mm-hmm.
optimization,
Yeah, yeah.
initialization could be better. So though this is not much used, but it led to
Yeah, yeah. So it's not
other,
used because we have other techniques which
yeah,
help us,
other, yeah,
yeah,
it,
train the
since
model better.
other techniques evolved, and sigmoid and
Mm-hmm.
uh, tanh.
Yeah,
Shall
so we
I
looked at
go?
tanh. Yeah, yeah. So we looked at tanh, sigmoid, and
Yeah,
then ReLU as well. Yeah.
ReLU. Yeah. So
Mm-hmm.
on the whole, leaky ReLU, exponential, and advantages, what
Mm-hmm.
each one had. So based on, I mean, we
Okay.
have to more or less ReLU will be
Yeah, ReLU
applied,
is used, yeah,
is
these days.
used, and but then initialization, uh, how not, I mean, how, what happens when it's initialized to zero, and
Zero, yeah. Or very large value. Zero or
or
initialized to the
same
same values. Yeah.
same value as a similar result, like
Mm-hmm.
uh, anyways, when we initialize to zero, the upper layers are all same values.
Mm-hmm.
It's not zero, but all of them have same values, and or if it is too high,
Mm-hmm.
so neither too
Okay.
high nor same
Mm-hmm.
nor zero.
Mm-hmm.
and then there was, I mean, some using variance
Yeah, so that is
some
timing
yeah,
initialization.
yeah, so
Yeah, so
it can do, I mean, instead of I mean, how to initialize. So
yeah, so that
mm,
variance across the layers
yeah,
are maintained. Yeah, so we don't have that vanishing or
yeah.
diminishing, exploding rate. Yeah. And then
Mm. Then batch normalization.
batch normalization.
That was
So
the
yeah,
last one was batch normalization. So
yeah,
every
so
batch, yeah,
every layer is forced. Yeah, so that
yeah,
the distribution of the activation remains
mm,
the same.
yeah,
So yeah, so yeah, thank you, Lita.
yeah,
So yeah, so let us go through all this, yeah, in more detail. So yeah, we so looked at pre-training first, then activation functions, weight initialization methods, and batch normalization. Okay, so yeah, so as Lalita said, yeah, we started with uh, pre-training. So why this was done was training a very deep neural network. It was found to be difficult. Okay, so that's why we do this pre-training so that we have a better initialization, so that optimization becomes easier. And this can be seen as a regularization technique as well. So we'll see why that's the case. Okay. So what people did was, yeah, yeah, so it was very difficult to train a deep network. So what is done is we want good initialization. So people did was so they took the first layer and then trained it using unsupervised objective. So 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 there are other ways of doing this as well, but we see how we can use that autoencoder, the loss function that we use in the autoencoder to learn this feature for this given network. So we first learn is using this objective function. So given the input, we are just trying to reconstruct the input again over here. So this is what we did in the autoencoder. Okay, so we trained this network. So we have some initial feature which has like a understanding of what the input is. So we then froze this H1 layer and then yeah, then try to reconstruct H1 again. So this way we learned like the features for H2. And this was like iteratively done for each layer so that we have good initial uh, representation so that yeah, finally to train on that. So for a given task, this entire network was trained on the given task on the final objective. Okay, so this is so this can be seen as better optimization as well as better regularization as well. Okay, so how regularization? Yeah, so the omega term which we had in the regularization. So there was the loss part L theta and this omega part, which is our regularization, and we jointly optimized both the thing when we saw the regularization techniques. But here you can see that these omegas are, so there are various omegas for each of the layers. So this is trained separately, and then after that we train on the final loss. Okay, so both the loss functions are not jointly optimized. So yeah, first we optimize omega and then we train on the final supervised objective. Yeah. So these are the some observation that we pre-training is more robust to random initialization. Yeah. Also leads to better weight initialization. So yeah. So after that, let us look at activation functions. Okay, so the technique that we discuss now, the supervised, unsupervised pre-training, this is not used, but it led to this activation functions and better activation function and better weight initialization. So yeah, so nowadays, yeah, so these techniques like compensated to this. So yeah, see. So to learn a non-linear decision boundary, we'll need a deep network with, yeah, relay activation. Yeah. So this is the first activation function, which is sigmoid. Okay, so this is the functional form sigmoid, and this is the derivative of it. So sigmoid saturates when the input is high. So gradient at, so for very high or very negative, very high positive or negative input, the gradient is zero. Uh, And also it's not centered around zero. So this is also an issue, because if we look at so if we consider this example, okay, this particular example, you can see the updates are, uh, for W1 and W2, it's either positive for both or negative for both. So this constrains the movement of the parameters, and it'll take longer time to converge. So this is an example. Then the second loss function that we saw was tanh. Okay, so this is centered, but it has the same issue of saturation. So for very high, so very large negative or positive values, the gradient is zero. This is centered. This is the derivative of tanh function. It's computationally expensive because we have to, sigma is also expensive. This is also expensive because we have to take e raised to x while computing this. And then, yeah. So this is the ReLU. Okay. So advantages does not saturate in the positive region, but in the negative region, again, the gradient is zero. But it has been empirically found that this works very well in practice. Yeah, it's computationally efficient. And yeah, so if the bias is very large, large negative value, then there's the issue of dead neurons. So, so that could be handled by better initialization, and yeah, other techniques like batch normalization and all will help us work around this issue. These are other variants of ReLU, like the leaky ReLU. Okay, so instead of for outputting zero for the negative values, it outputs a very small alpha times x. And yeah, computationally efficient, close to, this is not zero centered, close to zero centered. And there's exponential ReLU unit. Right. Okay, so before we move on, let us like solve few questions and again come back to this. So I'll read out the question and then, so which of the following activation function is not zero centered?
Sigmoid.
Yeah, sigmoid. Also, ReLU is also not
Is
zero-centered.
also not zero-centered.
So is softmax.
Mm. Only tan H has got negative values as well.
Yeah. So only tan H is zero-centered. So the answer is sigmoid, ReLU, and softmax. So that's clear, right? Yeah, let's move on. So what is the
Zero.
gradient of sigmoid? Yeah. Yeah, zero is the correct answer. So what are the challenges associated with using tan's activation function? It is not zero-centered,
Computationally
computationally expensive.
expensive.
Okay.
Uh, Saturation.
Yeah. So the
That's
first one is wrong because it's zero-centered.
mm,
So the second one is correct. Non-differentiable, it is differentiable at
it
zero.
is different. It's
So,
a smooth
so
curve.
this is again wrong. Yeah, saturation is an issue because a very large positive and negative value, the gradient is zero. So yeah, any doubts or questions? Yeah. For this doubts regarding this question or whatever we covered till now. So whatever we discussed over here also you can ask. And let's move on then. Which of the following activation function is preferred to avoid the vanishing gradient problem? Sigmoid, tan H,
ReLU.
ReLU, none of this. Yeah, ReLU.
Because sigma and tan H both have.
Yeah, for large values, for ReLU, for
Yeah.
positive values, yeah.
Is it?
For negative value, it will be zero, but yeah. So ReLU is the answer. Yeah, this is clear, right? Let's move on then. So we train our feed-forward neural network and notice that all the weights for a particular neuron are equal. What could be the possible causes of this issue? Weights were initialized randomly, weights were initialized to high values, weights were initialized to equal values, weights were initialized to zero.
Weights initialized to zero. Weights equal values. We just now said.
Yeah. So the answer is weights. Yeah. So when the weights are equal or
Equal.
zero, yeah. Hmm. So these two values. So these two options are correct. So the last two. Fine. Yeah, so let's see now what we covered in the initialization part. Okay. So yeah. So when we initialize all the weights to zero, okay. So we'll see that the gradients would be equal and the updates again would be equal. Okay. So yeah. So weight would again remain same, and the symmetry would not break during training. So that's why, yeah. So that's why you should not initialize weights to zero. Okay. And this is called
I have
symmetry.
a doubt in this symmetry breaking problem.
Okay.
I didn't quite follow, like what happens if it is, what if they are same? I mean, they have equal weightage. All features are having equal weightage across, not mathematically. Otherwise,
Okay, so
what happens? I mean,
okay, so
mathematically, I can see that the updates will be same, and there will be updates, but updates
yeah,
will be same. What
yeah, it'll be
happens?
same and all the weights. So if we take example of
Yeah.
this small example, so all the weights are going to be equal. So yeah, so somehow the network is like constrained, right? That is
Yeah, in
not
that
good.
lecture, it was mentioned that the weights are kind of tight, like the same kind of.
Yeah, yeah,
It's not so.
yeah. So
Didn't quite
training those.
follow.
Yeah, so training. So we could have like trained a very smaller network instead of that. So the tray, because we know the updates are going to be same. So if you are yeah, it doesn't make sense to learn those weights as well. So if we know that uh, yeah, all those weights are going to be the same. So yeah, it won't help us, right, in the training process to get some additional information about that. But yeah.
Yeah, thank you.
So yeah, Murthy, do you have a question?
Sir, is this document available for us? Can you share this?
Yeah, it's available on the
Okay, okay,
website.
okay. Sir, do you recommend any textbook to follow?
Yeah, so the recommended, so on the course web page, so there is one deep learning by Ian Goodfellow. So there are other books as well, like a deep learning book
Yeah,
by Bishop as well.
I
So
recently bought a book by Christopher Bishop.
so the new one, right? So
Yeah,
which
new
was
one.
yeah, that book is also good.
Okay, okay, sir. Thank you very much.
Mm. And so this is called the symmetry breaking problem. Okay. Now after this, we'll see what happens when the weights are very high or very low. Yeah. So here is a demonstration. Okay. So
Sir, sorry to disturb you once again.
uh,
Is this code available for us?
which code? This code in the lecture?
Yeah.
Uh, I don't think so. That is available. So you
So
The
how
code
do
can.
is
you?
actually in the
So
slide.
I
You
It's
never
in
can
the
just
slide
considered
deck.
copy
this
from
code
the slide. Yeah.
seriously, but unless we implement this, there is no point, right, in learning.
Yeah, 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 yeah.
It can be just copied from the
Yeah,
slide.
you can copy and run this yourself.
I don't think it's a full code. It's a piece of code, I think.
No, I think it is okay. So this has just the network, yeah. So the visualization part is not there. So that you'll have to
Yeah.
code it yourself.
So I think
Mm.
it's already ninth week, but I thought some code snippets are shared to us. Then that is going to be very useful, sir.
Yeah, yeah. So yeah, I'll do. So I have shared a lot of code which you can use. Uh, it's in the drive. Yeah. So today also we'll look at like few examples of network and how to initialize them. What happens when we apply batch normalization and all. So whatever demonstration I'll be doing here in the class, I'll share the code. It's so you can use that as a starting point and then run other experiments as well. So so here we yeah. So let us continue now. So here this is just empirical observation. Okay. So we are taking a network with 5 layers with 500 neurons in each layer and yeah. So the data points are sampled from this unit Gaussian distribution, and we'll see what happens. So we're not training, we are just doing forward propagation, and we'll see what is the distribution of activation that we get. Okay, you can see, yeah. So when the weights are, so yeah, so weights are very, very small. Okay, so as you go deeper in the network, you can see the weights have saturated. Okay, sigmoid and tanh. Okay, so it's close to zero. And when weights are too large, you can see again. So it's 1 or -1. So so it's uh, so instead of doing this, a principled way is, so this initialization is called timing initialization. Okay, the goal here is we'll try to maintain the, so we'll initialize the weights in such a way that the variance is maintained across the layers. So basically what we are doing is a bunch of multiplication and then adding all the things and outputting it. So yeah, so variance of this quantity is this. Okay, so we have this three terms, and we'll assume, so when we feed the input, we'll normalize the input. So this mean of the input is going to be 0. So these two again.
This sorry to interrupt. This naming convention. This S is actually the pre-activation what we normally do, right?
Yeah,
But
pre-activation.
why when they keep coming up with so many different convention, then it becomes confusing.
Okay.
Okay.
I don't, yeah, so
Yeah. Okay.
this
You
is
can
what
continue.
was there in the slide.
Yeah.
But so these are pre-activation.
Mm.
And yeah, and we just will look at the pre-activation because this is the place we are doing all the multiplication where the sum could like blow up. And when we pass it through the uh, non-linear activation, yeah, the values. So if the values are quite extreme, then yeah, we'll get 1 or -1 depending on what activation we are selecting. So that's why we'll look at this multiplication only, and we'll try to yeah, see that the variance is maintained. Okay, so the first two terms like would be 0, and we'll just focus on the third term. And for yeah, and for this to remain equal, okay. So yeah, so if we choose Gaussian and we scale it by number of input neurons, so this is how we'll initialize so that variance is maintained. Okay. So this initialization technique is called timing initialization. So it depends on the non-linearity as well, but yeah. So this is like a simple example that you're, so just to get an intuition key, initialization is important. Because there are papers on this to how to initialize depending on various activations we have. We'll look at that in the demonstration part. Right? Yeah, so after doing this, we can see the activations don't saturate with sigmoid and this. And for ReLU, we'll have to multiply it by a factor of 2. So it depends on the activation we have. Okay. And then finally, batch normalization. So instead of doing this initialization so that the distribution is maintained, so what other thing we can do is we can force this distribution. Okay, so that uh, across each layer, the variance and mean and variance is 0 and 1. Okay, so this is what is the idea behind batch normalization. And why this is done is suppose suppose the distributions are quite different, okay, during the training process, then it will be difficult for the model to learn, okay, after the update step, because yeah. Is that intuition clear key why if there is a drastic shift in the distribution across layers, it'll be difficult for network to converge, because suppose layer 1 has learned something, okay, now, after a single update step, if the distribution like of the final layer or layer above it changes, then that meaning of so layer of the distribution of the first layer changes drastically, then what it meant, the meaning of h1 would change, so then again the network will have to adapt, so that way the convergence would be slower. Okay, but this is we are so but there's other factor as well. So by uh, introducing this batch norm, we are forcing the network, like uh, constraining what the layers can learn. Okay, so yeah, so there are two counter forces, but yeah, empirically it has been observed that this helps train the network faster. Yeah, so we are for each feature, okay, so for each hidden neuron, so we'll compute its variance and mean, and then yeah, we'll normalize it like this. So this is done for the pre-activations before the activation is applied. Because yeah, and again in practice, so we have this extra parameters as well, which is uh, gain and bias, so that we don't force the layer to output just mean unit variance and zero mean. So it can, so depending on the input, these yeah, so it can choose whatever distribution it wants. Yeah, so this is an example where we saw using batch normalization, convergence is faster. So this was what was covered. So any questions or doubts regarding this? So yeah, let's solve questions again. So which of the following best describes the concept of saturation in deep learning? When the activation function output approaches either 0 or 1 and the gradient is close to 0, when the activation is very large and the close to gradient is close to 0, when the activation function output is, okay, so this was very large and the gradient is close to 0, or none of the above.
Can you make it bigger? Yeah, thanks.
I think it's 1.
Yeah, so the activation function output approaches either 0 or 1 and the gradient is close to 0. So yeah, so this is correct. Uh, what about the second one? Uh, so saturation means the network is not learning anything, right? So this is
So
also correct.
whichever gradient, wherever it is coming, gradient close to 0.
Yeah. Wherever gradient is close to 0, yeah. So I think the answer should be 1, 2, and 3, all three. So yeah, then which of the following is true about the role of unsupervised pre-training in deep learning? It is used to replace the need for labeled data. It is used to initialize the weights of a deep neural network. It is used to fine-tune a pre-trained model. It is only
To
useful for small data
initialize weight.
sets. Yeah, that's correct. So what is the main cause of a dead ReLU problem in deep learning? High variance, high negative bias, overfitting,
High
underfitting.
negative bias.
Yeah. So how can you tell if your network is suffering from the dead ReLU problem? Okay, so the loss function is not decreasing during training. The accuracy of the network is not improving. A large number of neurons have zero output. The network is overfitting to the training data.
Accuracy of the network is not improving.
Okay. Now that is not correct. So
This is
what does,
zero
yeah,
output.
so zero output is correct. It could be that, yeah. So large number of neuron have zero output. It could be that the accuracy is also decreasing, the loss function, yeah, improving, and loss function is also decreasing. But yeah, the
Both
definition of,
both 1 and 2 are same.
yeah, one and two are same. So yeah, so it's not the same. One is talking about loss function and the other is
Yeah, if the
accuracy.
loss function is not decreasing, the accuracy also not improve, right?
Yeah, it depends. It depends. It could be that loss function. So both are correlated, but there could be case when they are not following each other. So accuracy is the quantity that we are interested in normally. Okay, so if you take a retrieval or that, where you look at precision one, all those metrics, but those metrics are not differentiable. So you have like a proxy for that and have loss function like cross entropy and all. And it is not always that they'll follow each other all the time. Yeah. Yeah. So the correct answer is yeah. Third option is correct. What is the mathematical expression for the relative activation function?
Third one's
Yeah, max.
Yeah. The third one is correct. Yeah, the third one is correct. Yeah. So fine. What we'll do now is so we'll take a neural network and we'll see in practice like how. So we'll look at different initialization. Okay, we'll try implementing batch norm as well and see how the final accuracy of the network is
So this
affected.
code, where is it available? I was not able to get it. Is it in the YouTube
No,
description, or
no.
because this
Okay, let
it
me.
leads to the YouTube. The link leads to the YouTube.
Uh, Wait, let me show you how to access it. So you have to log into the, so once
Yeah,
you come here, okay, so here at the
yeah,
bottom, you have
correct.
this problem
It's
setting.
it's a recording is there.
Yeah, so this will take you to a Google Sheet.
Yeah, it's a
And
spreadsheet.
here, yeah, uh, so you, over here you have all the links to the
The
videos, and
YouTube
here
links. Yeah.
presentation folder links. So if you go here,
Okay. Presentation folder. I didn't go to the presentation. Oh,
so
okay.
here you'll get all the notebooks.
Oh, I thought it was
And
only presentation. Oh, okay.
I've
Okay.
yeah, so I have uploaded what we're going to cover
Okay.
today as well.
Yeah. Thank you.
Excellent, sir. Excellent. Thank you very much.
So yeah, so before moving on, let's take a break like for 5 minutes. I just use the washroom and come. Okay. Okay. Now let us continue. So first let me describe what the task is. Okay. So we'll train a neural network, but the task is we are doing a language modeling. And so language model is a task where we want to predict like next. So we are doing character level language modeling. So given like a set of list of characters, our task is to predict the next character. Okay. So the models like ChatGPT and all, so those are also a language model. Okay. But yeah. So let's see. So here I've saved the data. So let's see what's in the dataset folder. So we have like a bunch of names. Okay. And we'll train a model. Yeah. So it'll throw out names for us. So it'll throw out new names. And the way we will model it is given like a bunch of characters like this, model will try to predict the next character. So that is the task the model is trained on. And during inference, so we can start with like starting a token and then tell the model to predict until we encounter the end token. So that's how we can generate new names from our neural network. So is the task clear? So the language model that will train, it will generate new names for us. And this is the data set where we have list of names. Okay, so we have around yeah, 32K names. We'll use this, train a model, and then the model will output a new name for us. Is the task clear? The language. So this generation is called language modeling. Is the task clear to everyone? So here what I'm doing is I'm just reading the file. Okay, so the names file that we saw just now. Okay, and yeah, split lines too, because it'll read the entire file, and yeah, split lines will split it based on the next line character, and we'll have a list of words over here. Okay, so yeah, so we have 32 keywords that we saw. So if we look what is there in the dataset, you can see yes, there is a list of names over here. So what we'll do now is so the input to the model should be like a list of numbers, right? So we can't input characters. So we'll have to somehow map these characters to a list of tokens so that we can feed it to the model. So this task of converting is called tokenization. Okay, so because we are doing like character level, the number of tokens would be the different characters in the data set. Okay, yeah, so is this clear, the task now? So you've read the data set now. We have like a bunch of words. We'll have to tokenize this. So the way we'll do it is we'll just concatenate all the names and then see what unique characters are present in the data set. So because we are using just English uh, characters, so there'll be 26 characters, I think.
Is it each name one character?
So now the name is made up of words, right? So E is a character in the word. So now what I've done is I've read all the words which are different names. Okay, and a given name is made up of characters.
Okay.
Now I want to map this to map these two numbers so that I can feed it into the model. Okay, so that is what I'm doing here. So here I am finding all the unique characters which are present. Okay, concatenating all the names. So this function here concatenates everything. Okay, so we'll have like one. Know this Jupyter notebook.
And tokenization is based on each, you're leaving a space as when you're concatenating it.
Yeah, I'm not. Yeah, tokenization. I'll just find out all the different characters which are present there, and I'll assign a number to each of the different characters.
Yeah, so first is you are concatenating all the names.
Yeah, just concatenating all the names.
And no, when you're doing the
Just to find what unique characters are
tokenize,
present.
yeah, so each token is each character,
Yeah.
not
Not a word. Yeah.
not a
So
word.
not
Okay,
a word. Yeah.
character tokenization. Okay. So this is a small
Yeah, small toy
LLM.
example. Yeah, small LLM that we're training. Yeah. So ChatGPT and all are based on transformers. We are just using a two-layer neural network to do this modeling.
Good to learn small things.
So what happens here? I've just taken 100 characters. So basically what is happening here is so we are just concatenating all the names, and then when we apply set, we'll get like the unique characters which are present there. So here I'm just doing for like top 100 characters. So we'll get like unique characters. So that is what we are doing here, and then we'll map each of this character to an integer value. Okay, so that is what is happening here. Okay, so we are iterating over the unique characters, and then we have a map here from the character to the token number of that character. And yeah, so this is a special character that I'll use, okay, to denote the start and the end point of the name. Okay, so when we are so during inference, where when we generate a name from a character level language model, will will there has to be something, right? It has to output when we to indicate that we'll have to stop at that point. So
So
this
this is
character,
added to the dictionary. I mean,
yeah. So this is added to the dictionary. So in total, I guess we'll have 27. So vocab sizes there. So we have 27 characters, and and this is the mapping, how we are mapping each of the character to the tokens. So when we feed this, feed a given name to the neural network, we'll convert this into these numbers, and then we'll feed it into the neural network. So we have what we have done now is we have learned a tokenization strategy here. Okay, so we'll have to tokenize now so build dataset here. This function does that tokenization for us. So is everything clear till now? Okay.
yes, sir.
Yeah. Fine. So the way we'll model this is so there is something called block size. Okay. So given like the block size, so what the model is going to do is given some initial context, it'll try to predict the next character. Okay. So this block size decides the
It's taking 3 tokens at a time.
So it just takes three tokens at a time and then predicts the uh, next token. Okay, so we'll not look at all the tokens which it has generated, just the 3 tokens, and then based on that we'll predict the next one. So that is how we have modeled it. Okay, and so the final data set which is used for training the model is what we'll do is we'll take all the 3 characters. So our data set will be 3 characters plus the next one, whatever is present in it. So for Olivia, so number of training points we'll have is with Ollie will predict V. Okay, so that is one training point for this language model. With LIV will predict I, so that will be another data point. And similarly with Via, it will predict like the end character. So each of this will be a training point for the data. So we have a bunch of names, okay, but the way we'll model it to train the neural network is we'll take 3 characters at a time and try to predict the next one. So what will happen during inference is we'll start with uh, a start token and then tell it to predict the next word. Okay, so after it has predicted like three words, we'll use that and predict next word till it generates the end token.
That will become its new token.
That'll be the new. So I'm telling you what happens during inference.
Mm.
Okay, so yeah, so given three words, so is it clear what the data set is going to look like for this language model?
3 letters, no? Not 3
Yeah,
words.
three characters, letters, yeah. So the way we are creating the data set is, so we'll see all the three, we'll segment this into three characters and create like, so for a given name, like which is more than three, there'll be like uh, not just one data point for that given name, so there'll be more than one. Is that clear?
Yeah, I just wanted to clarify, like suppose Olivia, we took the example of Olivia. So initially, if I'm able to generate V, if I'm able to predict V,
Okay.
so my then OLIV will be my will be one token, right? And then you predict I mean, or not one token. You'll take OLIV and then you predict the. I mean, that will be your input. Sorry, OLIV will be your input, and I you will predict, and then OLIV I will be input and A you'll predict, right?
Uh,
No.
okay. So okay. Let me. I didn't get what you're saying, but so what will happen if you want to generate this name using the language model, right? We'll have
Mm.
to. So what the language model takes as input is three characters, and it predicts like one the next character. Okay. So to begin with, okay. So we don't have like any characters, right? Initially, when it starts generating.
Mm.
Okay, so for that, what we'll do is the extra character that we have, the dot one, we'll start with three dots. Okay, so we'll input
Mm-hmm.
three dots. With that, it'll suppose it's generating this. It'll generate O. Okay,
Mm.
so then we'll take two dots and O and predict L, and
Yeah,
then
yeah,
dot OL
yeah.
will, will predict
Got
I.
it. That's
And
what I was also saying.
once we have olive OLI, it'll predict V. So that is what happens. And when it predicts dot, so after VI, it will predict again, the dot again. That means we have to stop there. So yeah, so we'll remove all the extra tokens that we have, and yeah, so that is how the word Olivia is generated. So that happens during inference. Okay, so in the training set, we'll have this extra. So we'll have that dot predict O. So we'll have that point as well in the training set, and the two dots predicting L. So those are also data points which are created for this particular example. Okay, so uh, it's clear, right? So how we will create the data set and what happens during inference. Okay, so let's move on. So for each, so this function creates that data set that we just discussed. So it iterates over each word. Okay. Now, yeah. So the first data point is going to be just the extra token, special token that we added to our vocabulary. Okay. So three dots. So the extra token dot is has the token number 0. So we'll start with three dots, and with that, our task is to predict the first character which is present. So here we are iterating over words and then again iterating over character. Okay, and then creating the X and the Y data set. Okay, so for this context, starting context where we have all three zeros, yeah, we want to predict this Xi, and then yeah. So we'll add this Xi to the context now and remove the first character which was present there, and this is how we create like the data set. So it's clear, right? What x and y is going to be. So is this function clear? So what we discussed before, same thing we are doing over here in the code. So one extra thing that you're doing is we want that starting point as well. So that's why we'll start with all zeros, which is all dot, and try to predict, for example, Olivia will predict O. So that has also been added over here. So we are just creating all the 3-character, yeah. We're splitting this word into 3 characters plus the next word, and that will be our data set that our language model will be trained on. This is clear, right?
Yes, sir. Okay.
Yeah.
And we'll also create yeah, validation and test set out of it. Okay. Yeah. So here we have the 3 data sets: our training set, a validation set, and a test set. So this is how the training set looks like. Okay, and the corresponding. So this will be input to the model, 3 characters, and the output will be the single character that it has to predict using that. So using all zeros, it has to predict a 25. 25, I guess, corresponds to, so it's this E, I guess. Oh, it's some other character, yeah. So we are shuffling as well, I guess. That's why. Yeah, we're shuffling the words before creating this data set. So this is clear, right? So the task is given 3 characters to predict next one. And we have this additional trigrams as well. Okay. So now I'm defining a neural network over here. Okay. So these are the weights of the network. W1, okay, this B, W2, and this bias terms. So this is the two-layer neural network, weights of the neural network. In addition to that, we also have this embeddings, okay, that will learn for each of the character. Okay. So suppose if we look at this data set again, instead of passing these integers directly using this and multiplying with the weight vector W, okay, what we have here is an embedding layer. So for each of the tokens which are present in the vocabulary, it'll learn like a representation for each of the token. So 0 before passing through the neural network will be transformed. So we'll have a vector representing this 0 token. Similarly, for each of the character, we'll have like a so the size of the vector that I have taken is 10. And all these embeddings would be learned from scratch. So if we look at language model like ChatGPT and all, so those networks also have like a embedding layer. And yeah, so first we tokenize all the text. Okay, so once we have the tokens are then uh, converted to vectors using this embedding, and then after that further processing happens. So what we are doing here is we are like learning like a very high dimensional representation for each of the characters in our data set. So in case of language models like ChatGPT, it will be a subword level representation. So is this clear? What is happening here? So we have
So this one
defined.
is not subword, right?
This is character. So this is just character
Characters.
level. Yeah.
Yeah.
So for each of the tokens will have, so each of the characters will have like a token, and corresponding to that token there'll be like a representation that we're learning. So we'll pick that representation for each of the tokens. We'll concatenate it, and then after that we'll pass it through the neural network to make predictions.
In
Is
this
this
one, activation function is not there.
So I'm just defining the weights. Okay, so the network is not defined here. So these are just the weights. We'll have to multiply, and then yeah. So activation function will come here during training.
Okay.
So here I've defined we're just looking at the parameters of the neural network over here. Okay, and this G is like a uh, to fix the seed so that we get the same results, because these weights are randomly initialized. Okay, so yeah, so this is for reproducibility so that we get the same initialization every time. So yeah, so we're just looking at the weights, parameters which are present. So these are the parameters of the network. Okay, and I'm defining this requires grad equal to true, so that these are all PyTorch tensors. Okay, so we don't have to. So we just so PyTorch has this automatic differentiation built in it, so we don't have to compute the backward pass of it. So once the forward pass is defined, we'll get the gradients and the backward pass for the free. So it maintains a computational graph and does all the things for us. So we'll use that feature of PyTorch. So for that, to compute the gradient, we'll have to uh, yeah. So we'll have to make this requires grad attribute of each of the tensor. We'll have to set it to true. So that's what we are doing here. Okay, and the number of hidden neurons in a network is going to be 100. Okay, and the final this matrix that we have, okay, should be of the size vocab size. Okay, so hidden size is 200, but the output should be equal to vocab size, because it has to generate like characters, right? From this 20, the task is given 3 characters, it has to generate the next characters. Okay, so it has to learn a probability distribution over this 27, 27, right? So yeah, so this has to be, so these many classes we have. So you can think of this like a classification task as well. So given this input 3 tokens, we have to predict the next token to predict. So the output, so the final output should be a vector of this size vocabulary. So, and we can treat this as probability values, and then pick the one with the highest probability as the next word to predict. So there are other sampling methods as well, a greedy ways to during inference pick the one with the highest probability, treat that as the next token, and then use that as input to the model, and then keep on generating the new one. So the generation process is also iterative. So is everything clear till now?
Yes, sir. Okay.
Okay. Okay, so we have defined so these many parameters are present now in the network. Okay. So now we'll go ahead and train the network. So I have not done any, so I initialized using a random normal function. Okay, so I have not done the timing initialization or anything. Okay, we'll see we'll see how this network behaves, and then come with those initialization. Also here in the forward pass, uh, yeah, we'll implement batch normalization, and how we'll see how that affects uh, the learning process. Okay, so this is the training loop. Okay, so here yeah, we are sampling random like we're creating a batch over here. Okay, random indices, and then using that to index into the training in the uh, training data set. Okay, so we'll get the input and output over here. Okay, and then we are indexing to the embeddings, getting the embeddings for each of the token, concatenating here all the embeddings, okay, and then passing the concatenated embeddings uh, through the network, okay. So here is the matrix multiplication followed by the tanh activation that we're using, okay, and yeah, and this is the final. So then we'll pass this through through another layer and then apply cross entropy loss. So is this clear what the forward pass of the network? So let me ask you a question. Okay, so what should be the size of this concatenated embedding? So for a given data point, what would be the size of this vector? So this will be batch size cross some vector. So I'm asking for a given training point, what should be the size of this vector? This is what is passed through the network and will be used finally to predict the next character. So what is the size of this?
3. Whatever we.
Yeah, it will not be 3, some factor of 3.
Okay.
So could you explain like why? So this is all this step that is happening here. So yeah, so the 3 characters that we have. So you're correct. So we'll given 3 tokens, we'll predict the next one. But here we are indexing into the embeddings and then using those embeddings, concatenating those embeddings to get this final vector and then passing that through the network. Okay, so for each of the 3 tokens, we'll have like a vector corresponding to it. We are concatenating those vectors and then passing it to the network. So what is the size of the embedding vector? So it's 10, right? You have fixed it to 10. Okay, so for 3 tokens, we'll first index and get vectors corresponding to those 3 tokens. So we'll have like a uh, uh, vector with 10 entries for each of those 3 tokens, and we are going to concatenate that. So we'll get a finally for a given training point, we'll have a vector of size 30. That is what is passed through the network to predict the next token. Okay, so the size of this would be batch size cross 30 of this matrix. And the batch size that we have fixed is 32. So it will be 32 cross 30. So after this, when we pass through the first layer, because we have 200 neurons present over here. Okay. So the next, so what would be size of H then? So this is 32 cross 30. Okay. So what would be the size of H? So, so ask questions if you're not like understanding. Okay.
Okay, so we understood.
Okay, well, let's see step by step what is happening in the forward pass then. Okay, so we saw we have created this data set. Okay, it's having this 3 tokens, and will predict the next token, right? So for this case, we have this 0, 0, 0, and using that will predict the second one, right? So first, let me take this first character. So in the forward pass, okay, so we have this. Sorry. Okay, so using 3 zeros, we have to predict 25. So first step, what we are doing is we are indexing into the embedding space, right? So what we'll do is, and let's do that. So this embedding has size 20 cents. So for each of the character, there is a vector of size 10. So when we index into this, okay, so we'll get 3. So for each of this token, we'll get the corresponding vector. So we'll have 3 cross 10. Okay, so look at this size 3 cross 10. Okay, so 3 tokens, we are just indexing. So just indexing operation is happening. So with the token, we are just accessing the corresponding vector. Okay, and this is what we have. Okay,
Okay, this is
we'll then just concatenate all these 3 tokens, uh, vectors for the each other token together. Okay, so for that we are just so for this uh, we're just taking one example, so it will be 1 cross minus 1. Okay, so we are just concatenating those 3 vectors which are the output of this previous operation. So we have 3 vectors. I've just concatenated all those things, and what we have this at the end is this 1 cross 30. Okay, so this is for each day for a single training point. We have this vector output, and this is what will pass through the network. Okay, so we'll do this matrix operation. So W1 has size 30 cross 20. Okay, so when we multiply by 30 cross 30, so output would be 1 cross 200, right? So this 30 would get mapped to 300 activations. So this is what happens, right, in the neural network. So initially what we are doing, the examples till now what we had seen, we have some input, we just directly pass it through the neural network. Here there is just an embedding layer. Okay, so so the vectors corresponding to those tokens are learned from scratch. So there is just this additional step because we are dealing with text here. Okay, rest all things are same. So once we have this embedding vector, it will be same. So we'll just multiply this W1 with this. Okay, and yeah, we'll add 1 cross 200 dimension vector. We're going to add bias, pass it through tanh, and again going to do this operation. Finally, we'll have like a vector of size 27, which we'll then use to predict the next word. So is the forward pass clear now?
yes, sir.
So yeah, so this is the forward pass. Okay, and we'll call this loss dot backward on the final loss that we have, a single scalar value. So this will, because we are using PyTorch, it will create that computational graph during the forward pass, and when we call this function, it will accumulate all the gradients with respect to this loss inside this individual tensors. Okay, we'll go through, and this is the gradient descent step that you're doing. And after 1,000 step, I am just plotting the loss here to see what happens, and now I'm also keeping a track of the loss function at each time step, and we'll run this for 200k iterations. Okay, now let's see what happens over here. So let me initialize this again and run this training loop. Okay, we can see that it has started with this 28. Okay, and it's reducing now. So this is the same forward pass, but here, so once the training is done, we'll see what the final loss is on validation and the training set. Okay, it's the same forward pass, but yeah. So any questions or doubts regarding this?
Okay, sir, no doubt. More increasing.
Yeah, yeah. So let's plot and see what happens. So yeah, it's you can see it has started. So we have like this hockey stick like graph, right? Initially it started with very high value. Okay, then it has come in this sweet region, and then overall you can see it's bouncing up and down, but it's moving down. Look, if you see the trajectory, it's bouncing a lot. Okay, but overall it's moving. The loss is decreasing. Okay, so the hockey stick like graph that you are saying, this is bad. Okay, so what is happening? So the weights we didn't initialize it. Okay, so these were randomly initialized using this normal Gaussian. So what was happening in the initial part of the network was because we didn't initialize according to we didn't have a good initialization strategy here. Okay, so initial few iterations of the training was used to get this proper way, so after which the training process happens. Okay, so this is bad whenever we see this hockey stick like function, and this normally happens because of bad initialization. So we are wasting the like initial few training steps to arrive at good initial weights for that network. So we wouldn't see if we had like initialized using. So if the initialization was proper, then this we won't see this hockey stick like function. Okay. Now let's randomly see how we can do better, and then after this we'll apply timing initialization and see what happens. Okay. So normally we see this because the weights were actually very high over here. Okay. So let us make them. Let us make this weights. Let us multiply with a very small value and see what happens. Okay, using a very low value is also bad, and high value is also bad. So that's why the timing initialization was introduced. But we'll see what happens with this.
For
So
bias also you have to multiply.
bias, yeah, will multiply. So it's not required to multiply bias, but yeah, we'll multiply 0.5 to everything and see what happens. We don't want this hockey stick like behavior where the initial iterations are like wasted to 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 get a better initialization of the weights, after which the actual training process starts. Okay, we directly want to start from around like the 500K iteration, okay, so that the network converges faster. So let us record what the final loss is at this point. Okay, okay. So okay. Yeah. So with this random initialization, this is the loss we are getting. So we'll keep track of this as well. See how we can improve. So the next thing that you're doing is we observe that these weights that we started with are very high. So we'll try initializing it to very low value. And now let's see what happens. So you can see it starts with a better value now. So the weights were high initially in the previous thing. So now we have started somewhere better, okay. But we didn't initialize it in our principal manner, so we'll do that next. Okay, the training is done now. Let us look how the loss function looks like. You can see like this doesn't have that hockey stick like function. So it has so this there is bouncing back up and down, but overall the loss is decreasing. Okay, and yeah, the loss value also started with a low value because we have started with better initialization now than previously. So previously the weights were quite high. So now yeah, so the initialization is better and the loss is decreasing. Okay, let's see what the final loss is. Yeah, so yeah. So what has happened here is initially few iterations were like wasted to get the weights in the proper region. Okay, so that is not happening now, and yeah, so the loss function that we are getting finally is better than the previous one. Okay, so yeah, so let us can we like do better than this? We'll yeah, we'll use now chimeric initialization and see what happens. Okay, the same
So
thing that we
what should be the ideal loss function? What
so ideal loss function. Okay, ideal loss that we get. Okay,
is it?
yeah,
It
the
should be near
lower,
to zero.
yeah, the lower the better. But yeah, so reaching zero won't be possible in this case.
Okay.
Yeah, so zero is the minimum that we can reach because we are taking cross entropy, right? But yeah, so we won't be able to reach zero. I don't know what is the minimum that we can reach for this data set. So it depends on the data set as well. Okay, so lower the better.
Okay.
Okay, let's see. Let's open up the PyTorch documentary and see. Yeah, the chimeric initialization. Okay, so we'll have to multiply by that's the number of input yeah, input activation by gain also. This gain is dependent on the activation function that we have. So we are using tanh, so it will be 5 by 3. And this initialization has to be done just to the weight, okay, before applying the non-linearity. And in our network, we just have this one tanh non-linearity. So what we'll do now is, yeah, so we'll multiply just W1 with this, right? So it should be 5 by 3. So yeah, so this is correct, right? So yeah, so this was what was discussed. So this is a principled way of initialization. Initializing instead of changing this uh, changing this factor by a small amount and seeing how the network behaves. Initializing this the network this way is like a more principled way. Now, is this clear to everyone?
Yes, sir. Yes, sir.
Right. Now, yeah, we'll see what happens when we initialize it this way. Okay. And embedded. Yeah. So we have started somewhere similar as before. Okay. Because the 0.01 was like a good initialization for this given network. So you should expect somewhere similar to what we got. Could be better as well. Should be better because yeah, we'll see. Yeah, so the training is done now. We'll see. You can see the loss function is similar to before. And yeah, we are doing better than the previous initialization. Okay. Yeah, so initializing network this way,
Okay, sir.
yeah, it's better.
Not,
And
not testing. You can.
yeah, we were looking at different ways of initializing, and we saw that using this timing initialization or other ways, there is Xavier as well. So mm, using this converges the network faster because we have fixed the number of iterations now, okay, to 200K, and we saw that we arrive at the so this has converged like better than the previous. Yeah. So initializing a network is like very important for faster convergence. Okay. This is because we want to maintain the activations, uh, the distribution of activations in different layers. Okay. And initializing a network was very important before batch norm arrived because carefully initializing so that the distribution does not go haywire uh, was important. But now after the batch norm, the people like I also use these normal these initializations, but it doesn't initialization is not that after batch norm the networks are more robust to initializations. Okay, because we are forcing the network to maintain the distribution, right? So now we'll go ahead and yeah, implement batch norm. Okay. And so can like anyone tell me what should be done now? So we'll go ahead, where we'll have to add the batch normalization. So in this network, so we have this two layer network. We'll go ahead and implement batch normalization. So after which step should we put the batch normalization layer?
After H, we're calculating H and then
After calculating it, right? Yeah, you're correct. So can you tell me what should we do like to implement batch normalization? Just tell me what batch normalization is, and based on that, what tensors or what variables should I define? Okay, so that I can compute this. So what basically happens in batch normalization? Anyone?
we normalize the entire layer.
The activation, right? Across the batch. So for each,
Across. Yeah.
for each of the activation across the batch, we'll have to compute mean and variance, and we'll have to normalize. Okay.
Yes.
In addition to that, there were other two parameters as well in the slides, right? So there
Yeah,
was
there was one
gain,
formula with
gain and bias. So
yeah.
and those two terms were like learned from scratch, right? The network decided what the gain and bias should be. So for each of the feature, okay, we'll have to like have a gain and bias. So we'll have to define extra parameters, right? Gain and bias. So let us define that. So we'll need bias and gain. Let us initialize it to 0. And what should be the size of this tensor? Anyone, what should be the size of this tensor? It'll be one. So for each hidden layer, we'll have like one bias, right? It'll be this. And again, same. Is this clear?
Yes, sir.
So we have like these two additional parameters now. Okay. So one more thing to observe is, so when we have this batch normalization, this bias term here becomes redundant. Okay. So we can remove this bias, extra bias here, because we have already defined a bias over here. Okay. So we're going to add that to the normalized term, right? So then this becomes redundant here. Can like so what we'll have here is w into x plus b, right? And we'll normalize it and then again add this b. So this b becomes redundant. So when we are adding this bias, we can do away with this bias. So is this clear? So if you write down the mathematically you can see that this becomes redundant here. Is this clear why by adding this we can like just remove this bias from here? So is this clear why bias can be removed? because
Okay.
this the thing that it handles, this could be handled by this bias as well, the batch norm bias. So this is similar to when you have just a network with just linear layer W1, W2, W3. So those two W1, W2 can be modeled by a single matrix. So yeah, having uh, multiple layers of linear network is equivalent to single layer. So that you can see mathematically, this also is similar to that. So yeah, so this bias here doesn't make sense when you have this extra BN bias. So it'll be mathematically equivalent. So we'll just remove this from the network. And we'll add this extra parameters here for the gain and bias. Okay. Now is this clear? So what is it? So we have, so the number of parameters in the network has now increased.
Okay, sir.
Okay, so we'll have to compute mean across dimension 0. We'll have to keep them as 2 because otherwise the shapes of the gradient won't be consistent. So what we have done here is computed the mean. Again, we'll have to compute the standard deviation. Subtract with the mean. Divided by the standard deviation. Okay. And what should we do after this? We'll have to scale it up by gain, right? And add the bias. So is this clear to everyone?
Yes, sir. Yes, sir.
So this is the implementation of batch normalization here. Okay, so we are not done yet. We'll have to do any other things as well. But yeah, so this is what happens in the, this is just the forward pass of the batch normalization. Okay, so let us train the network now. Okay. So there is one important thing that we'll have to address now. Okay, so during forward pass, okay, we were able to compute this based on the batch statistics, right? So what will happen during inference? Okay, so it could be that during inference we just have one data point. Suppose we deploy this model, okay, uh, somewhere, and in real time we get a query. Okay, so at that time there's no batch, right? You just have a single data point. So we want to be able to compute this statistics there. Okay. So what we'll have to do is during inference, one way to do is what we'll do is we'll again pass through the entire training set and compute these averages for the training set and then use that on the test set. So first we'll do that and we'll see, and then yeah, we'll do that and see what the results are. So we'll have to compute this based on the training set and then use it for our test set. And we'll see how to do that efficiently during training itself. Any questions or doubts? So the training is done now. Yeah, so we have similar loss curve as before. Now we'll have to change this inference again over here. Okay. We'll have to add that normalization here as well, but so one way, well, we'll need that mean and standard deviation first. So for that, what we'll do is we'll again go through all the training points and accumulate those statistics first and then use that again. Now, when we use this torch.nograd, okay, what this tells PyTorch is for the code after this, we don't want to keep track of the computational graph. So that because we are doing inference here, okay, and we don't want gradients, and that takes a lot of memory. So yeah. So during inference, we'll use this. So here also I've used a decorator to tell PyTorch that I don't want to keep track of the computational graph. And yeah, let's calculate the statistics for the entire training set. Okay, so we'll have to do this step again. But here I'll have to wait for the entire training set and compute these statistics. Okay, is it clear why during inference we'll need this training statistics? Any questions regarding that? Because it could be possible in the training set. Yeah, we just have one data point and we won't be able to compute this statistics. We just mean over a bunch of training points. Okay, and we want the statistics, train time statistics to match that test time statistics. Okay. So during training, suppose we are doing classification tasks. Okay. So detecting dogs or cats. So we have features of dog and feature of cat. Okay. So during training, we are shuffling the data properly and then computing this mean and standard deviation. Okay. So the data set would have like dogs and cats during training. And suppose during inference, we just have images of cats. Okay, so what would happen is these statistics, the batch norm, mean, and standard deviation, during training and inference, it could be way different. Like, so we don't want that thing to happen. So if there is if what we are doing during the training is different from test point, so so that would not give the same results. So we want the training pipeline, testing pipeline to be similar to the training ones. So instead of using statistics on the test set, what we'll do is we'll go through all the training data points and compute the statistics on the training set as well, and then use those statistics during testing. So for that we are doing this. We'll see how better we can do this. Okay, but for now let's do it this way. So we'll go. So I'm taking all the training points and just doing the forward pass and computing the statistics for this activation. We have this mean. Okay. And we'll use that over here. So it'll be this same function. Okay, no, sorry. This should be added over here. Okay, so is everything clear now? What is happening? If you're not understanding, you can ask
Yes,
questions.
sir. Yes, sir. It is okay.
Okay.
Batch and this, all the things. Okay.
Yeah, let's compute
Clear.
the statistics again. Yeah.
Hmm.
Yeah. So as you can see, we were doing better before. So for this toy example, adding this batch normalization did not help. Okay, so yeah, so we are getting slightly increased
Right.
the loss, slightly increased loss than the timing initialization. But yeah, so we were doing then better than the when we are doing random initialization using heuristics. Okay, fine. So
Now testing or that.
yeah. So I've
Testing.
so I've changed the testing pipeline. I've added this batch normalization here as well, and yeah, we
Right.
are computing this loss again. Okay. So what we observe now, we had to do two forward pass through the network, right? So we did this. Okay. During training, we had to go through this, and after once the training was done, we again had to pass through the network to compute the statistics. Okay. So let's see if we can do better than this. Okay. So what we'll do is we'll instead of going through all the data points and computing the statistics again, uh, we'll do this during test time as well. So what we'll do is we'll keep running averages of this training, the statistics for data points, and then instead of doing this forward pass again, okay, we'll use those running averages directly during testing. Okay,
Okay, sir. Okay.
yeah, so that is an improvement. Okay, efficiency wise. So we'll go ahead and implement that now. So we'll have to keep running averages. Okay, so these are not parameters of the network. Okay, for mean,
So with this, you're adding zeros to the hidden network.
and also I just want to instead of computing this after the training process. Okay, so what I'll do is I just want to keep track of the statistics, running average of the statistics. Yeah, so I'm not adding any parameters. This is just like bookkeeping. I just seeing what the mean and the standard deviations are that we encountered during the training process for different batches. We're just keeping track of this running averages and will not do this forward pass again. Okay, to complete the statistics, we'll use this running averages directly during the testing. So the architecture wise, nothing's happening. We just yeah have initialized this to keep track of the mean and variance, so that we don't have to do this extra step during inference. And so yeah, I'll not add this running averages to this list of parameters. So this will not get updated during training. So these are not parameters of the network. Okay, and yeah, so here yeah, so nothing is happening here, just bookkeeping. So I'm just keeping a running average of this batch mean and standard deviation statistics for each of the uh, hidden activation. And then during inference, I'll just use I'll not use this, so we'll comment this out. Okay, and over here we'll directly use those running averages. And this is what is done actually in PyTorch. Now let us train the network again with this running averages. So it'll not change the training process. We'll get exactly the same because we have used this. Yeah, so we have used this seed. We have so that initialization is the same, and this will exactly get the same loss. But during inference, yeah, so instead of using this to compute the mean, we are using the running average directly, so that we don't have to do another forward pass through the entire data set. And we should get similar results like the before with the running averages as well.
can I leave it?
Yeah, okay. So this
Thank
is almost done. Yeah. Yeah, we'll end this. We are out of time. Yeah. So if you look at the plot again, it'll be exactly identical as before. Okay. The only thing is there's some mistake. Okay, so there are three ends. So there was a typo. Yeah, so we see we are getting similar as this, but this is more efficient implementation because we don't have to do this forward pass again. Okay, yeah. So there were other things as well to cover. We are out of time. We'll continue this next time. Okay. So here we just yeah. So I've shared the notebook. What you guys can do is so we just went through one initialization timing. Okay. So this PyTorch document has all the different ways we can initialize. Okay. You can see for this very small network. Okay, two-layer neural network how different initialization techniques behave. So there is this Xavier normal initialization, then there is Xavier uniform. So you can read about this, implement this for the small network and see how the different initialization differ. We can, so in this example, you've clearly seen ki using a better initialization will converge faster. Okay, so next what I wanted to cover is what happens when we have like a very large neural network. Okay, with like I think here there are five hidden layers. Okay, what happens to this when we have batch normalization? So effects of batch normalization show up when we have like a deeper network. He, so here we did not see much difference. Okay, for deeper network we'll clearly see batch normalization helps, and yeah. So so there was code to see how the activations of different layers behave. Okay. Yeah, we'll cover this next time. We don't have time now. But yeah, so I'll encourage you to first run this notebook till here and then try out different initialization and see how the initializations behave. Okay, so we'll continue from here next time. Okay. So any questions or suggestions how I can improve this session? So was everything clear today or fine? We'll end here then. Yeah. Thank you guys for attending. Yeah. Bye.